So this is AP Physics 1 with the Momentum 2 worksheet. We can see we're starting off with a graph that is force times time. And if we notice, the vertical axis starts at 0 and then goes positive from there. None of the forces are below the horizontal axis. None of them are negative. So from 0 to 3 seconds, will the object move to the right or left? So if the object begins at rest, we're going to say that from 0 to 3 seconds, if we give it a positive force, it's going to move to the right. Calculate the change in momentum from 0 to 3 seconds. Change in momentum is impulse. Impulse is force times time. From 0 to 3 seconds, looking at force times time, we're looking at the area under the curve. Area under the curve for this is shaped like a triangle, so it'll be 1/2 the base times the height. In this case, 1/2 times a base of 3 times a height of 8 would give us about 12. And we're multiplying force times time, so our units will be Newton seconds. At letter B, is the force positive or negative? All the forces on this graph are either 0 or a positive non-zero value, so it'll be positive. From 3 to 12 seconds, does the object speed up or slow down? Well, since the object began at rest and is moving to the right with the initial positive force, all the forces are either positive or 0, so from 0 to 3, we're applying a constant force, a positive non-zero constant force, so it would continue to speed up. It'll speed up anytime it has a non-zero net force. Or it'll at least change the velocity with any non-zero net force. From 12 to 18 seconds, does the object speed up or slow down? It's very tempting to say it slows down because the slope is negative, but the force remains positive. The force remains non-zero, so it will continue to speed up. Calculate the change in momentum from 0 to 18 seconds. The entire graph spans from 0 to 18 seconds. Change in momentum is impulse. Impulse is force times time. So we're going to look at the area under the graph for the entire span. Initially, we have 0 to 3. We've already calculated that as 12. We did that back in answer choice 1D. Then from 3 to 12, we've got a rectangle with width of 9 and height of 8. 9 times 8 is 72. And then from 12 seconds to 18 seconds, we have a triangle that would be shaped out. And here, I'll shade it in for you real quick. And the area of a triangle is 1/2 the base times the height. So 1/2 times 12 to 18 would be 6. And then the height still is 8. 1/2 times 6 times 8 is 24. We'll need to add each of these areas to get the entire area under the curve. So we have 72 plus 12 plus 24. And that's going to get us the 108. And of course, Newton seconds. The last question says, if a 5 kilogram object was moving 2.5 meters per second before the impulse shown, calculate the final velocity. 5 kilograms is the mass. 2.5 kilograms is the initial velocity. We're looking for the final velocity. Now, when looking at this, we know force times time is impulse, and we know mass times the change in velocity is also impulse. We can set those equal to each other. Force times time, or impulse, change in momentum. That's what we found in the previous problem, 108 Newton seconds. We've calculated that. We can set that equal to mass times the change in velocity. Force times time is equal to mass times change in velocity. We calculated force times time in the previous problem. They gave us the mass of 5 kilograms. And we're going to look at the change in velocity, v minus v naught, final minus initial. So we got that 5 is our mass. 108 is equal to 5 times. We're looking for the final velocity, and we're going to subtract the initial velocity. 108 is equal to 5 times v minus 2.5. So we've got 108 is equal to 5v, just distributing the 5, minus, oh, hold on, this is going to kind of be in my way, so let's clear out a little bit of the work we did before so we've got room for the work we're doing now. Distributing that 5 times negative 2.5 should get us negative, is it 12.5? Yeah, I think it's 12.5. Here we can just do the simple algebra. We can add 12.5 to the other side. So if we have 108 plus 12.5, we would have 5v is equal to, should be 120.5. Isolate v by itself. We're just going to divide both sides by 5. When we do that, v is going to be equal to 24.1 meters per second. We've got our final velocity. Now let's clear all this work out so we've got some room, less clutter. In the next section, they've given us, think of it like a ball going down, hitting the ground and bouncing back up. On the way down, we've got a negative velocity because we'll call down negative. And then as it goes up, we'll call that a positive velocity. Yes, they're both marked positive, but we understand that negative is directional, so is positive. So the first one, we have a negative 12 initial velocity because it's 12 down, and a final velocity of 10 with a mass of 48. If we're calculating the impulse or the change in momentum, we would have mass times the final velocity minus the initial. So 10 minus negative 12. There we get a 1,056. For the second one, the initial velocity is negative 18. Final velocity is 16. With a mass of 35, we have 35 times 16 minus negative 18 because it's final minus initial. So you're subtracting a negative number. We get 1,190. For the next problem over, we've got V naught is negative 20 initial velocity. V equals positive 20. So we're going to have 16 times 20 minus negative 20. And we do that, we get 640. For our last one, our initial velocity is negative 24 because it's 24 down. Final velocity looks like it's positive 20 with a mass of 27 times final velocity of 20 minus negative 24 is equal to 1,188. It asks us to rank the above masses from greatest to least magnitude. It's not asking necessarily for the greatest in magnitude of mass, but the greatest in magnitude of impulse that mass experienced. I believe that was really the theme of what it's asking, or the intent of what it's asking. So which one has the greatest magnitude of impulse? As we look across it, it looks like the second one with 1,199. So that's the 35 kilogram mass. The next largest is the 27 kilogram mass at 1,188, followed by the 48 kilogram mass at 1,056, and then finally that 16 kilogram mass there at the very end. The last problem we have at the bottom, there are two cars collide and stick together upon impact. The first car, mass of 1,000 kilograms, was initially moving at 20 meters per second. The second car, mass of 1,500 kilograms, was stopped at a stop sign. Let's start with drawing our free body diagram. We've got mass 1 in a box, and we've got mass 2 in a box. Well, instead of doing it mass 1, mass 2, let's go ahead and put the actual masses in. It'll be a little bit easier to visualize what's going on with those. So 1,000 kilograms in our free body diagram, I guess. Not really, but anyway. 20 meters per second going to the right. Then we've got our second object at 1,500 kilograms and its initial velocity being 0. My dashed line just indicates where the collision is. The left side is the before the collision. The right side is after. And I'm combining the masses. I've got 1,000 plus the 1,500. So a total mass on the right of 2,500 kilograms. And I believe that's moving at 8 meters per second there to the right. If we're looking at the momentum before is equal to the momentum after. Which car experiences the greatest force? We know this from Newton's third law. They experience the same force but in opposite directions. When two objects interact, the force between them is the same, but they'll be in opposite directions. Which car experienced the greatest change in momentum? Change in momentum is impulse. Impulse is force times time. Well, they have the same force. They have the same time. So if they have the same force and the same time, they have the same change in momentum. As far as magnitude, yes, it will be in opposite directions. C, what is the impulse experienced by each car? We know it's going to be the same in opposite directions, but let's go ahead and calculate it and just take a look. Impulse is change in momentum, so we can calculate it as either force times time, or we can do it as mass times change in velocity. According to the information that we have, mass times change in velocity is going to be the best route. So mass times final velocity minus initial velocity. 1,000, open parentheses, final is 8, initial is 20, so 8 minus 20. I get negative 12,000 Newton seconds for the first car. Second car, I've got mass times the change in velocity, final minus initial, is equal to 1,500 times the quantity 8 minus 0, final minus initial. And that should give me 12,000 as well, but this one's positive, the other one was negative, and both are in Newton seconds. If the collision took place over 0.5 seconds, what was the force experienced by each car? We know the force is the same, so we're going to say 12,000 is equal to the force times the time. We've got the impulse, the change in momentum, 12,000, and that's equal to force times the time. They gave us a force. We're just going to divide that 0.5 to the other side to solve for force, and when we do, we get 24,000 newtons. Again, that's the magnitude. One of them received a positive 24,000, the other one received the negative 24,000. Finally, if the collision took place over 0.5 seconds, what was the acceleration of each car? Since each car has a different mass, they're going to have a different acceleration. Mass times acceleration equals force. They share the same force with different masses, larger mass, smaller acceleration. Here we know the initial velocity for car number 1, V0, is 20 meters per second. Final velocity is 8. Time is 0.5 seconds. And we're looking for the acceleration. I think the easiest thing for me to do when I see these particular variables, I love VOTAT. It's the only kinematic equation with a name. So we have V equals V0 plus A times T. Kind of looks like V equals VOTAT. 8 is equal to 20 plus A times 0.5. We're going to subtract that 20 to the other side. And then we're going to divide by 0.5, and we get negative 24 meters per second square. Ooh, that should be a meters per second square for the acceleration. Don't worry, I'll fix that here in a second. Number 2, I've got V0 is the initial velocity is 0, started at rest. Final velocity is 8 meters per second. Time is 0.5 meters per second. 0.5 seconds. And the acceleration is what we're looking for car number 2. We're using the same kinematic equation, V equals VOTAT. 8 is equal to 0 plus A times 0.5. Solve for acceleration. We get 16 meters per second square is our acceleration. And let's go over and fix that on the other as well. Negative 24. That finishes up the front. We've got half this page done, half to go. What do we have? 2 eggs, 0.25 kilogram each, are dropped from the top of a 20-meter high building. Each hits the ground with the same velocity and stops. So they're dropped, so the initial velocity is 0. We know they're going to accelerate based on gravity. They're going to hit the ground. But we're coming out of the energy unit, and we're feeling a little bit better about energy than kinematics. So let's use energy to solve this. Our initial energy is gravitational potential. Final energy is kinetic. We've got 1/2 mv squared is equal to mgh. Masses cancel out. So gravity times the height is equal to 1/2 the velocity squared. We've got 10 for gravity times 20 height is equal to 1/2 v squared. So 200 times 2 to get rid of the 1/2. We would have 10 times 20 times 2 would be, 400 is equal to v squared. And then the square root of 400 is 20. So 20 meters per second is that final velocity of each egg before it hits the ground. We saw masses didn't matter there. For B, what is the change in momentum of each egg? Well, we know that change in momentum is force times time, and it is also mass times the change in velocity. So we can decide either side of that equation to use. Mass is 0.25 kilograms. Final velocity is 20 minus 0, because the initial velocity was 0. We can calculate that, and what do we get? Should be 5. 5 Newton seconds is our impulse, which is change in momentum. Was the impulse experienced by each egg? That's what I just said. Impulse and change in momentum, they are the same thing. We've already calculated change in momentum, so we know what the impulse is. 5 Newton seconds. Impulse equals change in momentum. Don't let it fool you. If you prefer one over the other, if you see the opposite, just scratch it out and write it in the one you prefer, because they are the same thing. Looking at D, the first egg hits the ground and stops in 0.002 seconds. The other egg is protected by a drinking straw scaffolding and stops over a time of 0.05 seconds. What is the average stopping force experienced by each egg? By changing the time, we're changing the force. The change in momentum is the same thing. They're still coming to a stop. So the product of force times time is going to be the same thing, but by increasing the time, we're decreasing the force. Think about driving. Slam on the brakes, a lot of force. Ease on the brakes, less force. So force times time is 5. We saw that before. This time we're going to say force times 0.002 is equal to 5, because we've entered in an actual time. We divide 0.002 over, and what do we get? 2,500 newtons. This is for the one that had the very short stopping time of 0.002 seconds. So that egg experienced 2,500 newtons of force. For the second egg, where the time was 0.05, a much longer, relatively, time period, the force is going to be much less. 5 divided by 0.05, we should get about, I think it's 100? Yes, 100 newtons. So it's a big difference, 100 newtons of force compared to 2,500 newtons of force, just by changing the time from 0.05 seconds to from 0.002 seconds to 0.05 seconds. Which egg has a better chance of surviving the fall? Egg number 2, the other egg, where it says the other egg that's protected by the drinking straws apparatus. The very last question, where we've got John and Jim driving identical 1,000 kilogram cars. So in our diagram, we've got John, our initial velocity is 30 meters per second. Jim, initial velocity is 30 meters per second. They're both coming to a stop. So they've got the same initial momentum, 30 times 1,000, mass times velocity. Coming to a stop, at a stop with 0 velocity, we're going to have 0 momentum. Mass times velocity is momentum. Change in momentum is negative 30,000. Final minus initial. 0 minus 30,000, negative 30,000. Jim has the same thing. He's starting with a 1,000 kilogram car going 30 meters per second and coming to a stop. So he also has a change in momentum, or an impulse, of negative 30,000. So we've calculated and labeled the initial momentum of each. When they stop, what's their final momentum? Did that. Calculate and label the momentum for each car. I think it means change in momentum for there. We've done that. Which one had a bigger change in momentum? They had the same change in momentum, right? They both had 30,000. They both finished with 0. So they both had a change in momentum of negative 30,000. Which one took more time to stop? Well, John stopped over a 50-meter distance where Jim did 25, so John took longer to stop. Which one needed a bigger force? Jim. As we reduce the time, we increase the force. Reducing the time increases the force. Which one had a bigger impulse? It's the same impulse, because change in momentum is impulse. We agreed that the change in impulse was the same, the change in momentum was the same, so of course the impulse is the same. Using a kinematic equation, find the time for John to stop. Well, the initial velocity is 30 meters per second. Final velocity is 0 meters per second. The change in position was 50 meters. And we're looking for time, so we don't have acceleration. So we'll use the equation delta x is equal to 1/2 times v plus v naught times time. So delta x is equal to 1/2 v plus v naught times time. Let's put in 50 meters is equal to 1/2. And then v plus v naught is just going to be 30 times time. So 50 is equal to 15 times t. And we get 3.33 seconds to find the time for John to stop. If Jim's brakes apply 18,000 newtons of force in stopping, calculate his stopping time. So change in momentum is equal to force times time. The change in momentum was negative 30,000. Time they're giving us is what we're looking for. We rearrange, we'd have time is equal to change in momentum over force. So 30,000 divided by the force of 18,000. Yes, it was a negative 30,000, but the force would be a negative 18,000 to stop, because a positive force would just speed us up. So negative 30,000 divided by negative 18,000, or 30,000 divided by 18, is going to give us 1.67